Hi, I'm Tyler Whitaker, first year PhD student in the Neuromechanics Lab at University of California, Irvine. Thanks for clicking my talk, where we'll be looking at how increased slip and fall risk influences locomotion priority in guinea fowl. So most analysis of locomotion assumes steady state, where velocity and mechanical energy are constant. But locomotion in the real world is complex and non-steady, involving substrate interactions, maneuvers, and obstacle negotiation. And these real-world interactions introduce trade-offs and task-level demands, where things like speed, economy, stability, and injury avoidance must be balanced, influencing locomotor strategy. In the real world, failure to balance these translates to injury risk, while in the wild, it can mean life or death. Guinea fowl have been shown to be a useful model for studying non-steady locomotion, from terrain height perturbations to different substrate interactions. However, little is known about how guinea fowl plan and adjust locomotor behavior over multiple step navigation tasks, such as turning maneuvers. So here, we investigate locomotor dynamics and turning maneuvers in helmeted guinea fowl on both high and low friction surfaces, and we are interested in how they adapt their locomotor strategy depending on task level performance constraints and priorities. So to test this, we recorded 10 trials for each of 7 guinea fowl, negotiating 4 different runway conditions, varying in either orientation, bent versus straight, or substrate, our control, or lined with polypropylene, our slippery substrate. For the rest of the talk, I'll be using the following icons to ID the different runways. Here, control turns, CT, control straight, CS, slippery turns, ST, and slippery straight, SS. So each runway was lined with a 6 force plate array, highlighted in red, collecting force data as the guinea fowl ran from starting box, this box on the left of each runway here, to the end box, the box on the right. And to encourage them down the runway, in a timely manner, they were safely followed by various household items, in this case a mop, which to guinea fowl can be quite encouraging, although it's not very scary to us. To frame our expectations, we use a simple point mass model for turning. So for running around a bend, a change in velocity heading involves acceleration perpendicular to the original velocity heading, requiring a lateral force. And if the total velocities remain the same, there must also be a net deceleration on the axis of the original heading, a net negative fore-aft force. And the force impulse required in each direction can be calculated based on impulse momentum balance if the change in heading and initial velocity are known. These equations tell us is that faster speeds or sharper turns result in higher changes in mean force per step. And the figures below shows how this plays out over a range of speeds, denoted by this color gradient here, where dark blue are faster and this green is slower, and changes in heading on our x-axis, with increase in mean force per step on the y-axis, assuming a fixed step length, speed, and stance duration. And what we can see here is that large changes in heading, large turns, require very high forces, and as do faster speeds. And so from this, we can make a general prediction that due to the required maneuvers on the bent runways, we'll see slower speeds on the bent versus straight runway orientation. And again, we can say that slippery terrain will be slower than controlled terrain, but to frame the predictions for the substrate interactions on bent runways specifically, we'll use a case study comparing direct approach and gradual approach. In the bottom left, we'll add a top-down view of the runway to visualize the different paths. So each of these cases has a total change in heading of 90 degrees, but they differ in change in heading per step. This direct turn has a per step change in heading of 45 degrees, taking 2 steps to complete the turn. In the gradual case, the change in heading from step to step is 15 degrees each, taking 6 steps to complete the turn. And we have the mean force, change in force per step annotated here, where red corresponds to the direct turn and green corresponds to the gradual turn. And what we can see here is that the sharp turn requires increases in mean force per step up to 2 body weights of force, whereas the gradual turn requires half that. However, if executed at slower speeds, the force requirements are much more reasonable, even lower than the force requirements for the gradual turn. So broadly, turning is limited by either the capacity to produce force as constrained by structural limits or by the coefficient of friction. On our control runways, these limits aren't really of concern, and the direct approach would be most pragmatic. albeit at much slower speeds than straight runways. But our experimental runway, since slippery surfaces constrain the maximum force in these direction relative to the vertical force, we expect an exponential increase in the risk of slipping in direct approaches. And thus we expect a similar response to offset this risk, notably slower speeds, shorter steps, and shallower turn angles, most likely approximating something like this gradual turn here. And so for our slippery turns versus our control turns, we expect much slower speeds and much shallower turn angles. And here we'll summarize our predictions for how sharp they will turn and how fast they'll go on the different runways, using the same table as before in the introduction with these icons. And the CS condition is going to be our reference condition, so everything is in reference to our control straight. And we'll use arrows to indicate the directionality of the changes and the size of the arrows to indicate how large those changes would be. So for our bent versus straight runways, we expect much slower speeds, denoted by the length of these arrows here, than our straight conditions. And we obviously expect them to turn, given the fact that it's a bent runway and that turns are required. For our slippery versus control terrain, in our straight runways, we expect moderately slower speeds and probably slightly more gradual turns due to the friction limit. But on our bent runways, due to the compounding constraints and requirements for turning and the lower friction limit in slippery terrain, we expect there to be a fairly sizable effects. So much slower speeds in our slippery turns compared to our control turns, and likewise smaller change in heading per step. Here we have a video from a trial on our control turn, and it shows the data that we're going to be using for our results. So on this first figure here is center of pressure, medial lateral on the y-axis, fore aft on the x-axis, and we can see the step at touchdown with each of these dots. And then on this figure here, we have ground reaction force and body weights over time. And we integrate the force data for velocity and position for estimates of center of mass. So transitioning from a side view to a top-down view, here we have a plot of all trials for one subject for our control turn condition. And if we just hone in on one trial, we can see the medial lateral and fore aft positions of the center of mass at touchdown for each step, which are the dots. And those are our first two measures in our analysis. And then each of these dots have a velocity, which is our third variable in our analysis. And a key variable that we'll discuss is the change in heading with each step. And using an example where we have red as a first step and then green as a second step, the center of mass has an initial heading at touchdown for this first step in red, and then a final heading in the subsequent step in green. And we can get a measure of how much its velocity heading changes from step to step, and thus a measure of turning, by taking the difference of heading for the subsequent step minus the initial step. And that's our final measure in our analysis. And we fit these data into a linear mixed effects model with our fixed effects laid out here. So we have runway condition as a grouping variable, and medial lateral and fore aft positions also grouped by runway condition. So we get a coefficient for each condition for each of these. And in the case where heading was the dependent variable, velocity was included as a covariate. So first we'll look at change in heading for the condition effect, which is the effective condition when accounting for the influence of the other effects. And what we can see is that in the slippery straight condition is not different from our control straight, but there is a difference when turning. So they do turn less sharply than the control straight, but not more so than the slippery straights on average. When looking at the effect of fore aft position, it's what we would expect with the change in heading increasing as they go down the runway. So they are turning near the end of the runway in control turns and slippery turns, but these effects aren't significantly different. So they basically turn about the same. Now looking to velocity and our runway condition coefficients for velocity, we can see that SS is slower than our control straight, so they do mitigate speed a little bit on the slippery terrain here. And in both turns, they mitigate their speed significantly compared to straight runs. This is different between both of straight orientations. However, although they do go slightly slower in slippery from control turns, instead, the explanatory power is absorbing the position coefficient. So looking at fore-aft position specifically, what these coefficients tell us is that they are, in control turns, they're speeding up as they go down the runway versus slippery turns where they're slowing down. And so we'll unpack these results in the framing of our predictions, with our original predictions to the right, and we'll also add our trajectories for control turns and slippery turns to the left with these top-down views for all subjects in these conditions. So looking at turning strategy, guinea fowl did not modify turning strategy as much as we'd expected. There's no difference in turning strategy between the bent runways, and our position coefficients didn't indicate that they're turning towards the end. So basically, most of the turns are occurring here, but they're in equal magnitude. What we saw instead was a speed-mediated strategy, and so they went slower in turns compared to straight runs, and they slowed down slightly more in slippery terrain compared to our control terrain in our bent runway orientations. But these differences weren't significant. Instead, what we saw is that in control turns, they go faster as they go down the runway, so they speed up, versus our slippery turns where they slow down. And so they opt to decelerate in slippery turns to limit slip and fall risk, even though they have the same turning strategy. So what's next? Well, there's a lot of variables that we didn't get to discuss today that will be included in our final analysis, including the changes in forces and changes in spatial temporal gait parameters like step length and step duration. And we're also interested in individual variation in strategy and its influence on learning. So some birds slipped and fell, but they managed that pretty well. And so they kind of mitigated that disturbance response, while others didn't, and they chose to avoid falls altogether. And so this individual strategy is in this variation is interesting, and so that's something that we're going to be looking to explore. And this kind of hints that maybe that there's different that different birds balance and juggle priorities differently. Where risky birds might be okay with falling, and more reserved birds choose strategies where they avoid slips and falls altogether. And in line with that, we're interested in the strategies for disturbance rejection, slips and falls. In the future, we'll be using Deep Lab Cut, which we have a video of our working model here. And so using kinematics, we hope to explore how do they mitigate that disturbance when slipping and falling so that they can continue traversing down the runway. So thanks for tuning into my talk. If any of you have any questions, you can contact me here, and thanks to all of these people who have helped me out along the way.